Good afternoon. I am Chanda Devnath, one of the PMRF fellows. So, in this course, I usually discuss about some questions based on this topic called organics, retrosynthesis and problem solving approach. Till now, we have discussed all different type of named reactions, important ones, and different other reactions, how to approach our desired product. So we have already discussed all these named reactions and some many more also which are not mentioned here. Then we discussed some olefination reaction and some reaction of double bonds, followed by some reactions where we do not need any kind of reagents like the thermal and photocatalytic reactions. So today we will discuss some retrosynthesis of some important molecules using all these reactions which we have learned till now. So let's start. So first, what is retrosynthesis? So retrosynthesis is a technique chemists use to identify how to synthesize a molecule through approaching the problem backward. Like if you are given a molecule, a large molecule, now you have to plan how to prepare this large molecule for a simple reagents we usually have in our laboratory. So for that we will plan a backward pathway, like from where we can synthesize this large molecule. Effectively, retrosynthesis starts from the wanted product and works backward, chopping the changing and molecule into smaller pieces. These chopped up molecules referred to as synthon and usually unstable ions. Thus, it's important to identify the more stable equivalent molecule which could be react the same way. The trick to good retrosynthesis is knowing which bond to be broken, and unfortunately this is something that comes from practice. So retrosynthesis totally is based on how we can predict, how we know how much we are aware of the organic reactions and how they go through, so that based on that we can plan a retrosynthesis. There is no such tricks to plan any retrosynthesis of any molecules. It's totally based on your experience. So a retrosynthetic arrow is used to show a retrosynthesis in taking place. Is like this bold arrow. Suppose you are given this molecule. How will you plan the retrosynthesis of this molecule? So whenever you see any kind of functional group, we will target that. So here there is a keto group and there is a alkene group. So if we just break this alkene, there are two bonds are broken. So there will be two negative center, and in the another side there will be two positive centers. These are called synthons. These are called synthons. Or if you just go through one single, suppose you just have broken one bond, one among these. one among this double bond. Okay, just one bond, one negative charge and one positive charge. Now two, so these are the synthon, these are called synthon. So synthons are the unstable species. Synthons are the unstable species which we get unstable ions. Okay, so these are synthons. So what are the synthetic equivalent? So they get to satisfy this negative charge. How can, if we just add a proton here, and to satisfy this positive charge, if we add a because we just broken one bond, so it's still connected to it with a single bond. And to satisfy the positive charge, if you add a OH here, okay, so this is the synthetic equivalent. Now if we just break this bond also, in the similar pathway we will add another H at this position, there will be added 2H, and for this part there will be added 2OH. Now we know that geminal OH is not stable. There is no such compound with a geminal OH, because whenever there is a geminal OH, it will undergo the hydrolysis. So it will give us a geminal OH is not possible. It immediately undergo water elimination to give us this ketone. So this is the retrosynthetic pathway. So what will be the forward synthesis? We just have to take 2 molecules of this one, 2 molecules of cyclopentanone. If you adjust base, it will undergo this, which is what type of reaction it will go through? It will go through the aldol condensation pathway. We have learned about this reaction, aldol condensation. So if you know how to, what is aldol condensation, you can plan the retrosynthesis of this molecule. How will you plan the retrosynthesis of this molecule? How will you plan? I just give 2 seconds, just think. I just give one hint which bond will be broken first. This bond. This is a hint. First is, so there will be a positive charge and there negative charge. Negative charge will be compensated by hydrogen. So it will be give us a alcohol, and it will give us a, if you just add a leaving group, the positive charge will be compensated. Now how will you form this compound? So if you just break from this place, then a positive charge here and a negative charge here. How we can now can you say how we can generate a negative charge at this ortho position of this ester group? What type of reaction can be possible here? How we can incorporate this methyl ester group, this ethyl ester group to this position? How is this possible? So this center can be generated from, if we just add a bromine here, in presence of zinc, it will form a zinc bromide that act as a nucleophilic center and can attack to this position. So this is, so if we it can attack. There is another probability if you just add H and there is a aldehyde. Another probability is if you just this is one type of retrosynthesis. Another probability is this one. If you just add a H here and in presence of base, it will create a enol intermediate and that will attack at this place. Okay, so retrosynthesis can be more than two ways. Whichever is preferable for you, can, because to synthesize a molecule there can be different ways are there. So what will be the forward synthesis of the retrosynthesis of this molecule? How will you prepare this molecule? So if you just, so this is the protection, if you can see this is the protection. If you just break this one and you will get 2 OH plus acetone. In the next step, if you just functional group interconversion, if you just change this aldehyde, alcohol to aldehyde or ester and break this bond from this place, then there will be a positive charge here that can be compensated by adding a OH and there will be a formation of aldehyde, and there will be a negative charge here that can be formed through this Reformatsky reaction, which you have already discussed. You can just add a bromine at this place. Two ways are possible. You just add a bromine at this place and in presence of zinc it will form a zinc bromide complex and that will act as a nucleophile. Another is if you just add a H and in presence of base it will form a enolate and that will react with our aldehyde to give our desired product. Okay, so this is the forward synthesis. If you add a zinc bromide and ethanol, it will attack to the ethyl aldehyde, and through reduction it will undergo, it will be a alcohol, and through protection of two alcohol with acetone will get our desired product. Okay, so you can see whatever reaction we have read till now, based on that we can plan a retrosynthesis of any molecule. How the relationship of this alkene and the carboxylic acid influences the suggestion of the synthesis of these three compounds. So all these are 3 carboxylic acid with a double bond in a number of carbon in the long carbon chain is same, but just the position of the double bond is different. So what will be the retrosynthesis of 3 molecules? Obviously it will be different for 3. What are they? So I will show this one. First, so there is a double bond here. If you just break this double bond from this place, it will be like CO2 ET. So by Reformatsky reaction, we can form one carbon bond at this center, then from here to here, then through elimination of water it will give us this alkene. So what will be this is our backward synthesis. So what will be the forward synthesis? Forward will be the first step. You will add this CO2 ET, as all this reaction is simple and already discussed, so I am not going into the mechanism in details. We are just, if you have any confusion you can ask, but I am just giving how we can plan. So if we just add all this, it will go through a Reformatsky reaction and form one carbon-carbon bond. After that, through elimination of water, so if you just add H plus, just H plus and heat, it will eliminate one molecule of water, and this ester will be hydrolyzed and we can get this as our product. Okay, what will be here the retrosynthesis of this case? Suppose if you just break the bond at this place, then it will be a allylic carbocation and the CO2 minus. So the source of CO2H the easiest source of CO2H can be CN. So we add just a bromine here to undergoes allylic substitution, and the source as a source of CO2H, if we add CN minus, which we can get from KCl. or CuCN. So this Cn minus will attack to this carbon to substitute bromine. Then through hydrolysis we can get this CO2H group. What will happen in this case? What will be the retrosynthesis of this one? So if you just break the bond from this place, so you have to, which bond will be broken is just based on your experience. We have to find to that bond to be broken where we can, if you add any functional group, you can plan a retrosynthesis. So if you just break this bond, there will be a positive charge here that can be compensated with a with a leaving group, and there will be a negative charge here that can be compensated with a bromine. Or H. So if it's a ester, so in presence of base it will undergo the enolate formation. That enolate, this enolate would react with this one to substitute this bromine. After that through hydrolysis we can get this one. Forward synthesis I think it's clear, so I am not drawing it. You have to just, if you add this compound to this one in presence of NaOH, like base, so in presence of base it will form a enol. That enol will react with this allyl bromide, substitute the bromide. After that, if you perform hydrolysis, CO2 will be hydrolyzed to acid. What will be the retrosynthesis of this molecule? So we'll just break the carbon oxygen bond. So it can be an acid, and this positive charge can be compensated with a alcohol. In the next step, if you perform a Birch reduction to get this diene from a benzene, if you perform a Birch reduction, we will get this one, as it is a electron donating group, because carboxylic group is not directly connected to the benzene ring. So as it is a electron, just a methyl group, so has a plus I effect. Whenever there is a plus I effect group, the double bonds are drawn like this way. I have already discussed about a dedicated class on Birch reduction. You can go and check the problems there, then you will idea how we can determine how to place the double bond when it is electron donating group and or it is electron withdrawing group. Here is the acid group, but as it is one carbon apart, it acts as a alkyl group. So it has a plus I effect, so you will consider that, and it will Birch reaction, you will get this product. In this case, if you just if you just break this bond, and add a bromine here, and instead of CO2H we can add KCN or CuCN. And this can be prepared from if I have a double bond here, in presence of Simon-Smith reaction, it forms a cyclopropane. We have already discussed that in presence of Simon-Smith reaction it will form a cyclopropane. So in presence of Simon-Smith reaction it will form a cyclopropane. How we can prepare this double bond also, that I have already shown here. If you just break this, add a triple bond here and break this bond, you will get this from acetylene and aldehyde. Just note it down so that you can plan how the reactions are going through. You can get idea. Just for saving time I have already drawn it. What will be the retrosynthesis of this molecule? So if you just break this from here, then there will be a sulfur nucleophile and you can add a bromine at this place. So first we just add a bromine at this place, and there is sulfur nucleophile. The next step, we do functional group interconversion, and we change this bromine as alcohol. Now in the next step you just break this bond, first if we can, we just do a functional group interconversion again. And make this a ketone. just break this bond. So what will be the forward synthesis of this one? First, aniline will be react with this acyl chloride to form this amide. After that, if you undergoes a Fidelcraft acylation, this acyl group will incorporate at the para position of this amide group. Next, if you undergoes a reduction, this will undergoes as it is a amide. If you add NaBH4, amide will not get reduced, but the ketone will. So ketone will be reduced to alcohol, and through bromination reaction, it will undergoes a bromination and it will form CBr bond. And after that, if you add a thiourea, as sulfur nucleophile will be incorporated here, and we will get our desired compound.
Excuse.
Yes.
Hello.
Yes.
Yes, ma'am. Here, one methyl group. Starting material aniline, right?
Yes.
So, how where this methyl come?
Actually, there is a this methyl group will not be here. It's just mistake. Is it okay now? This aniline will form this one. After that, if you perform Fidelcraft acylation reaction, normal Fidelcraft acylation reaction, how it goes through, if you know, it will react. These two will react with itself. It will form this acyl cation, and AlCl4 minus, AlCl4 minus. Then this aniline can attack from this para position to this to form this. Now there are two groups. One is amide, one is ketone. If you add NaBH4, it will undergo selective reduction of the ketone, and through bromination, selective reduction of ketone to give us alcohol. This will be transferred to OH, and if you undergoes a PBr3 bromination, the OH will be substituted with bromine. In the next step, if you add thiourea, that will act as a nucleophile and substitute the bromine. Now if you add NaOH, thiourea will be hydrolyzed. Thiourea, you know, no? This is urea. This is called urea. And this is called thiourea. If it attacked from this sulfur, it would form this next step if we add NaOH. This will give us I just jumped one step. First the OH will attack here, this bond will open, again the NH2 will lone pair will comes back and will break this carbon sulfur bond to give us this thio product. Okay. So this is a question from CSIR net. What is the correct sequence for the conversion of this to this? From this 4 option, which will be the best to prepare this cyclopentenone from this diketoester? So if we just plan the retrosynthesis first and break this carbon-carbon double bond, then there will be a 2 positive charge here, through negative charge here. To compensate 2 positive charge, there will be 2 OH. 2 OH means it leads to a carbonyl. And there will be 2 H. Like this. This can be possible through a enolate formation. So if you just break this carbon-carbon double bond, okay. So now let's draw the forward synthesis of this one. Between these two ketone and ester, which one is more electrophilic? Obviously this one. So to now we want to, this is more electrophilic. Now just to get a product from this ester molecule, we first have to protect our ketone. First have to protect our ketone. So the forward synthesis will be first you have to protect this ketone. So for that we need the ethylene glycol and H plus. So which of the option has, so already these two are cut. These two have this ethylene glycol. The next step, we want to make this ester group to alkene. For that we need Tebe reagent. We have discussed about this Tebe reagent earlier also. So we need Tebe reagent to make this ketone to alkene, ester, carbon oxygen double bond to alkene. We need Tebe reagent. So which one has Tebe reagent? This one, because Wittig is not for ester. Wittig reagent is only for ketone and aldehyde. So between these two, which one will choose? We will choose this one because it has Tebe reagent. Wittig is only for ketone and ester. So the correct option is this. So this will be from alkene. In the next step, if you just add H plus, what will happen? This will be deprotected. This will be the next step. This comes here. And next step, through elimination of water, we will get this ketone. I think this much you can draw by yourself. Then through elimination of water, okay. So the correct option is option A. How we can prepare this alcohol from this bromide in 3 steps. So we have to plan the retrosynthesis such a way that we need 3 steps. So first we will just break this bond. And there will be a bromide. Sorry, it should be, I just jumped the steps. There will be a negative charge and there will be a positive charge. That can be generated if you make this aldehyde. This becomes a positively charged electrophile, and to make this carbon a nucleophile, we add MgBr, Grignard, which can be prepared easily from alkyl bromide and magnesium. So I think forward synthesis is very simple. If you add magnesium to this alkyl bromide, it will form this Grignard reagent. This Grignard reagent has a delta, sorry, I just missed one carbon. This Grignard reagent has a delta negative charge at this place. So this will react with our aldehyde and form this alcohol. So it is in 3 steps. First step, this one. This is the second step. So within 3 steps we can prepare this compound. How will you prepare this from this? So there is a 2 carbon extension. Molecule is same, just 2 carbon has been added inside this carbon chain. How we can prepare this? We just plan the retrosynthesis. you just so in this way, if you undergo, so what will be the forward synthesis? If you perform a hydrobromation, the bromine will be boronation, hydroboronation, boron will be added to the less hindered side, and hydrogen will be added to the more hindered side. Then it undergoes, if you hydrolysis through H2O to NaOH, this carbon boron bond will be converted to carbon oxygen bond. Then through ketone tautomerism, it will give us this ketone. If you perform a hydrolysis, this ketone, this aldehyde will hydrolyze to alcohol. After that, if it would react with this acetylene through elimination reaction, through substitution reaction of this OH group, it will give us this as our product. Okay, you can add one step here also. Before OH, you can add here a bromine, because between OH and bromine is a good leaving group, so you can add one step here. So this is the backward synthesis. Forward synthesis, you guys try by yourself at your home. So if you have any issue, whatever reagents you need, if you have any doubt, you can ask me in the next class. All these reaction I have already discussed in all my classes. So this will be hydroboronation reaction. This will be hydrolysis of carbon boron bond through H2O to NaOH. For this step, it will be just a tautomerization of ketone tautomerization. For this step, it will be a hydrolysis. Sorry, this will be, it is a reduction. After that, if you just convert this OH group to a bromination, then if you just react with this acetylene through SN2 elimination, it will give us this as our product. What will be the retrosynthesis of this one? So if you just break this carbon-carbon double bond, it is 2 ketone. Now how we can prepare ketone from alkyne? For hydroboronation, you always get for terminal alkyne, you will always get a aldehyde. But for terminal alkyne, if you perform a demercuration reaction, it will give us a ketone. So because the addition is just opposite, so addition is Markovnikov in this case. I have already discussed. If you have any doubt, you can ask. So if you just perform, you place a double bond at this place and OH here. Sorry, double bond at this. Mercuration. And the so this is same. So by this process we can prepare this alkene from this alkyne. So the first will be mercuration, oxymercuration, oxymercuration, demercuration, then it will give us this ketone, and after that if you undergoes a Wittig reaction, it will give us this alkene. So if you just for the first step, if you just protect this ketone, then perform all this reaction, at last you have to deprotect it. So this is the forward synthesis. First you have to protect this ketone, because otherwise there will be two ketone. At a point you will have two ketone. So for selective Wittig will be difficult. At a point you will have two ketone. So in this step you can't perform protection reaction, because both ketone are similar. So for the first step you have to protect this ketone, then perform all this oxymercuration demercuration reaction, and it will be a Wittig reaction of this ketone group. It will go CH2. In the last step you have to deprotect it. So these are the tricks you have to. So if you just protect, you can't protect it from this step, because two ketone will be the similar nature, so you can't protect it selectively. That's why you have to protect it from the first step. So this is the forward synthesis. Whatever forward synthesis I am not drawing, try by yourself. If you have any doubt, you can ask me. How will you plan the retrosynthesis of this molecule? So there is two probability, if you can break this bond or you can break this bond. So if you, I am just drawing the probability of A. Suppose you are breaking bond from here. Whatever retrosynthesis you are planning, you have to see which plan has less problems or less chances of side reaction. That retrosynthesis will there will be a negative charge here. A positive charge at this place. So this can be compensated if you add a bromine. So it can undergo the SN2 reaction, eliminate the bromine to give us our desired product. Another probability, that is path B. Then there will be a positive charge here and negative charge on sulfur. To give a diphenyl bromide. So what is the case? In this case, there is a probability of a side reaction where amine can attack itself and eliminate the substitute the bromine. So there is a probability of two types of product, where sulfur will attack and one is nitrogen will attack. So as there is a, so there can, it will give a mixture of product. mixture of product, where in one case sulfur will attack, in another case nitrogen will attack. But in this case there is only one product is possible where the sulfur will attack at this place, so the correct pathway will be pathway A. Okay, so from this question we have understood that there is a probability of two types of retrosynthesis. We have to choose that one where there is a less chances of getting mixture of product, because there is no chance of getting, there is only one nucleophilic center here, so it will just attack itself. The nitrogen can't attack with bromine because it will be an intramolecular attack and it will form a cycloaziridine type of ring, so that is not possible. So it's a 3-member ring, that is not possible. Because of that, its sulfur will attack here and it will form this as our desired product. What will be A and B? So I hope you have get an idea how to plan a retrosynthesis of any compound. So now we'll discuss some of questions like how to predict the products. So if you what will be A and B? If you perform bromination followed by hydrolysis, it will give us a trans product. Because it will form a bromonium ion followed by cleavage of the bromonium ion, so it will give a trans product. Like one will be, if the OH is in above the plane, bromine will be below the plane. In the next step, if you add excess amount of ammonia present to reaction, as they have mentioned excess, that means both of the group will be substituted. So our product B will be, as both of the product is getting substituted, the amine will attack from the below the plane here and amine will attack from the above the plane here. So one amine will be so there will be an addition of two amino group. One amino will be below the plane, another will be above the plane. So this is our A and this is B. What will be 1? So if you perform lithium aluminum, if you add lithium aluminum hydroxide, what will happen? This ester will be hydrolyzed, ester will be reduced to and followed by H plus, so it will be reduced to alcohol. So it will be reduced to alcohol. In the next step, so this is 1. In the next step, if you perform tosylation, it will give us OTS. In the next step, if you get base, there will be formation of alkene. Now, if you add chlorine, chlorination followed by hydrolysis, there will be formation of chloronium ion. And as they have already mentioned, there will be two products. That means one is where OH will attack at this place, another is OH will attack at this place. So there will be a mixture of product. So this will be our 4 and 5. This is our 3. This is 2. What will be the products all these alphabets? So let's first solve this one. If you perform the mercuration followed by reduction, it will give oxymercuration, demercuration. It will give us this will be our first it will form a cyclic carbocation with cyclic mercury cation. H2O will attack. At this place where the carbocation will be more stable. Next, the mercury group will be reduced by NaBH4. So this will be our A. In the next step, if we add H2SO4, this will be H2O, and through elimination reaction to give us alkene. Now if we add osmium tetroxide H2O2, it will form dihydroxylation. Of the alkene. This is our B. This is C. Okay. I am keeping this as a homework. You guys can try by yourself. I will solve this in the next class. What will be A, B, C and D? You can check. You can take a snapshot of this problem and try by yourself. What will be A, B, C, D and E? So let's go step by step. If you do MCPBA, it will undergo the epoxidation. So to plan whatever product is forming, the way we can, I am drawing the product in a just one second. For that you have to know, you have to have an idea of all these type of simple reactions and what we have discussed till now. So this will be A. Next, if you add NaOH, this will be hydrolyzed to give a diol. We add NaOCl. Both of them would be chlorinated. The next step, we add Grignard. what will be the product A, B and C. So if you undergo the ozonolysis reaction of this so this one probability is double bond get ozonolysis or the triple bond. Which one will undergo the ozonolysis reaction?
And can you repeat the last one?
This one. NaOCl, I hope I discussed about NaOCl can act as a oxidizing. NaOCl can act as an oxidizing reagent. So as these two OH are there, so both of them will be oxidized here in this case. That's a doubt. So both of these will be oxidized. In the next step, if you add Grignard, it will be OH and there will be a methyl group here. Okay. In the next step, if you have H2SO4, there is a proton here. So at this place there is a double bond here. In a similar way, there is a double bond will be here. Thank you for noticing this. That's why here NaOCl will act as an oxidizing agent.
Ma'am, one more question. Go through the previous slide where chlorine bridging the epoxide form bridging chlorine. Next, or previous. Previous one. Yeah, yeah, yeah. Here, I
Here this is a chloronium ion, like a bromonium ion, like a chlorine will come here. Cl
OTS form
O,
and adding chlorine, these chloronium ion will form.
no. After OTS there is a formation of double bond. Like I just
Yeah, yeah.
after
This one
OTS
part.
there is
And
a
then,
elimination of the OTS group through base through this NaOH tertiary butoxide sodium tertiary butoxide base. There is a elimination of OTS. Okay,
okay,
that will
okay, okay.
that will give a alkene. After that, if you add a chlorine here, it undergoes a chloronium ion formation, like double bond will attack here and the chlorine lone pair will attack to this again to this double bond and this will eliminate it from the system.
Okay.
So it will form a chloronium ion. After that, when the H2 is there, H2 can now chloronium ion has two electrophilic center. One is this one and this one, like epoxide. So it can attack both of the center. When there is one product is shown, suppose instead of 4 or 5, if there is just 4 given, then you have to go for the product which is more stable or the more probability to form. But when there is given as 2, so you have to show both of them. Suppose now between these two, which will be the major product and which will be the minor product. So if you just open this, as this going through a SN2 kind of pathway. So for SN2, always attacking to a 1 degree carbon or less hindered carbon is more favorable. So whenever this is attacking at this place and this is opening up, that will give us our major product. But if it going through a bromonium type of thing, then it will go through a SN1 type of mechanism. In that case, it will give us this as our major product, depending on the mechanism. Here I just missed one thing. This NaOH will act as a oxidant. For this is selective to 2-degree alcohol. Selective to mainly 2-degree alcohol. Whenever there is a 2-degree alcohol, these are always used for oxidation. So the correct here, this E will be this will be your E. Okay, for this one, if you undergo epoxidation, ozonolysis reaction. Now the ozonolysis reaction is based in presence of Me2S. So ozonolysis are two types. One is under oxidative condition, another is on neutral condition. So if you had Me2S, it's under neutral conditions, it will not undergo further oxidation. So in that case, it will give us a aldehyde. So this alkene will just give us aldehyde. And this ketone, and this is alkyne. Will give us a ketone. If you perform ozonolysis of alkyne, it always give a ketone. Suppose just keep this carbon center fixed and only break one carbon bond and add two oxygen here. In that case, you can plan it. Mechanism is bit difficult. You can go and check in any book. You can get the mechanism. Now in the next, so this is our A. In the next step, they have added NaBH4 methanol. So NaBH4 reduction will be selective reduction between ketone and aldehyde. So if there is ketone and aldehyde, it will selectively reduce our aldehyde. So this will be selectively reduced. I have a confusion at this step. 1 second. Yeah, there will be an acid. It's not a acid.
What if man? Hello.
Yes, I am drawing the mechanism. Do it.
Yeah.
Suppose it's for alkene. I think for alkene, you know that if you have a alkene, We add ozone. I'm just drawing via a simple one. You can wait so that it is not complicated here. So if we add ozone in this one, it form a this type of intermediate. Next, so this there will be a bond cleavage. I'm not, it will go to this center. Actually this is undergoes a ring bond cleavage and then addition again. I'm not drawing it in a descriptive way. You can go and check from a normal ozonolysis mechanism. First this bond will break. Okay, first this bond will break and it will form a peroxide and there is oxygen. Then there will be a recombination by which it will form this type of species. There will be a cleavage of this bond. Again recombination will give this type of species. In the next step it will again undergoes a cleavage type of thing, by which we will get two molecule of aldehyde. For simplicity, we don't go into the mechanism. We will just break this double bond and we will add two oxygen. So the mechanism is a bit difficult, so I am not going into details. But in case of alkyne, in first just consider it like a cleavage of one double bond. Suppose cleavage of one double bond. Then what it will give? You suppose if it is cleavage of one double bond, then there will be a keto group here. Still there is a sigma bond which is connected to both of them, and there will be another keto group here. That will be like this, right? Because if any double bond breaks, there will be addition of two ketone at this place. Suppose between two double bond, one double bond is getting broken. So there will be a keto bond here and a keto here, and there is the preliminary sigma bond is already still there. Now in place as the reaction is in presence of oxygen and this ozone and H2O in medium, it will give us a acid. In medium it undergoes a cleavage and give us a acid. So whenever there is an alkyne in presence of ozonolysis, it will give a acid, and alkene will give us a aldehyde. Now in presence of H2, this is our A. Now in presence of NaBH4, this aldehyde will be reduced to give us this alcohol, and in presence of H2SO4, this OH will attack to this place and eliminate. And give us this lactone type of moiety. Now they have given the molecular formula, you just have to count it. Carbon 5, hydrogen 8, there will be 2, 2, 2, 4, so it will be 8 hydrogen and oxygen 2. So the molecular formula is also matching with this one. Okay, so from this question which we have learned, if there is a double bond through ozonolysis, we will get two molecule of aldehyde or ketone. But in case of triple bond, we always get a acid. We will always get a acid through formation of this dicarbonyl compound. It will undergo the hydrolysis in medium in presence of ozone. It will give a acid. Okay. So this much for today's class. If you guys can try this one by yourself, we'll solve it in the next class, and I will try to add more retrosynthetic questions in the next class. So, thank you.